So yeah, I'm your host Hassan Banahimel again. Welcome to Linear Algebra for AI and ML Day 13. I'm Hassan Banahimel, currently studying in Department of Computer Science in BRAC University. Today is our Day 13. Today is 30th May 2024, and this session is supported by Global AI Community Dev Changemakers NSDC and TensorFlow User Group Bangladesh. So, what is our concluding session's topics? So, in our today's session, we will be discussing about the trace operator and the principal component analysis. So, at first, let's jump to our the trace operator. So, yeah. So, what is the definition of a trace operator? We learned about the matrix. We have seen what is a matrix. In a matrix, there, if we have a square matrix, uh, let's assume we have a matrix A, and it is a 2 by 2 matrix. So we have a 1, 2, 3, 4. So here in this is called the main diagonal, right? So if I choose to find a trace, I will sum the elements on its main diagonal. So what will the trace of A? So the trace of A will be, here I have 1 and 4, so it will give us 1 plus 4 equal 5, and where notation is tr, and in the braces we have a. So what are the properties? It has linearity and cyclic permutation invariance. Here we can see the tr of a plus b, tr of a, and plus tr of b, and when we are doing it with any scalar, our scalar will be multiplied with our the trace of a. And how we can do the cyclic permutation invariance, it will be trace of AB will be equal trace of BA. When we next to our next slide, here we can see the applications of the trace operator. So what are the applications of these trace operators? It can be characterizing matrices, it can be used in quantum mechanics, it can be used in statistics. In the characterizing matrices related to eigenvalues and matrix properties, we learned in our previous sessions how to define or how to find eigenvalues and eigenvectors, and how to find the matrix related properties, right? So in that sessions we learned about traces, and in the quantum mechanics it is used with density matrices and operators, and in the statistics it's used in multivariate statistical tests. Now let's see some code about this one. Let me change my screen. Here we are working on Google Colab. Google Colab is um, powered by Google. Here you can do the data science or this kind of mathematical problems or Python codes. So it is denoted at tier of A, and simply the sum of the diagonal elements of matrix is summation of I and A of I. For this part, we will be at first importing our numpy to do these mathematical terms, and we are defining an array in the variable of A. Here we have a 2 by 2 matrix. It will be 25, 2 in first row, and in the second row we will be getting a 5 and 4. So when we run this cell, we will be getting an array of 25, 2 and 5, 4. And we seen in the slide that our trace will be the main diagonal, summation of the main diagonal. Here in the main diagonal I have 25 and 4, so this will be the trace. So when we run this for like as usual, it will give us 29. So we can also find a trace in the numpy using np.trace of a. You will be getting the trace. It is also giving us 29. The trace operator has a number of useful properties that come in handy while rearranging linear algebra equations, such as transpose of A will be equal transpose of A transpose, assuming the matrix shapes line up transpose of ABC will be equal transpose of CAB and will be equal transpose of BCA. In particular, the trace operator can provide a convenient way to calculate a matrix's Frobenius norm. We learned earlier that how we can find the Frobenius norm. So that was for the matrix trace operator. Now we will be moving to our slides again. So now let's start our journey in principal component analysis, or PCA. So what is the definition? PCA is a statistical technique used for dimensionality reduction while preserving as much variance as possible. It transforms the data to a new coordinate system where the greatest variances come to lie on the first coordinates, or the principal components. And what is the objectives? It reduces the dimensionality of the dataset, it identifies new meaningful underlying variables, and it also reduces the computational cost, and also it removes noises. What steps are involved in here? So when we highlight this with the highlighter, it standardizes the data, ensure each feature has a mean of 0 and standard deviation of 1. It also compute the covariance matrix, identify the covariance between different features. It helps you to compute the eigenvalues and eigenvectors. We learned previously on how to compute the eigenvalues and eigenvectors. It determines the principal components. It helps you in sorting the eigenvalues and the eigenvectors. It When we were doing the computational maths on eigenvalues and eigenvectors, we have used the PCA to arranging the values in the descending order of the eigenvalues. It also helps in the projecting data, transform the original data set onto the new set of principal components. What are the properties in the PCA? The principal components are orthogonal. That means it all are uncorrelated. The first principal component accounts for the maximum variance in the dataset. We will be watching that later in our code, and in there finally we will be subsequent principal components account for the remaining variance under the constraint of orthogonality. And what are the applications in our data compression, reducing the number of variables in a dataset? It also helps in visualization, representing a high dimensional data in 2D or 3D space. It helps in noise reduction, filtering out noise by ignoring the components with lesser variance. And it also helps us in the feature extraction, identifying important features that contribute most to the variance. So why we will use this PCA, or everyone have, like, we have human natural, like, why we will be using that, what are the advantages we can use rather than this, we will be using that, or something like that. So everything has some advantages or disadvantages. What are the advantages of the PCA? It simplifies the complexity of your data. When we are working with a big chunk of data set, it simplifies the complexity of your given data. It also enhances the interpretability, and it also improves the computational efficiency. And everything has some limitations, we all know that, right? So it also have some limitations, or you can also say it at a disadvantage. The first one is the sensitive to the scaling of data. it can sometimes lose important information if the variance is not a good metric for the underlying structure, and sometimes it not suitable for nonlinear data relationship can be addressed by kernel PCA. Now again, let's move to our coding slide. uh, Here we're again working with the principal component analysis. At first we will be importing from sklearn, we will import our datasets. We will be loading the iris data. When we run this one, our data will be fully loaded. Yeah, so now let's find the shape of the data. Here we are having four rows, four 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 columns and 150 rows. So let's at first get the feature names. What are the features we are having? uh, we are getting, at first we will be getting the length of sepal, we will be getting the width of the sepal, we will be getting the length of the petal, and we are getting the width of the petal. So to more explain, we are doing this for a flowers dataset. So when we are running this one, we will be getting a 4 column and 6 rows dataset. We are getting a 5.1, 3.5, 1.4, and something like that. This first column indicates as the sepal length in centimeter. The second column uh, shows the sepal width in centimeter. In the third column, it is showing the petal length, and the final one is showing the petal width. So again, in from sklearn.decomposition, we learned about decomposition earlier. We will be importing the PCA, and also we will be using matplotlib to plotting this whole one. We imported this one, and now let's PCA. We will be decomposed with the best two components, and we also done the transform in a variable called x. Here you can see that now we got the 150 row, and we got the best two one to transform or to fetch the data to the perfect one. Now when we run this, here you can see that we have got a two column. This is the best two columns which will help us to get the most precise or the most perfect values, or to predict which one is showing us or which one will be helping us to find the accurate one. Now let's plot this one. Yeah, so here you can see we are plotting these data here in our matplotlib, using matplotlib. Here it is plotted, and now do the target shape. It will be doing the 150 rows. And now let's do this in array. We got the array, and now let's find an array for the unique elements, the counts elements. So here we got a 3 by 2. Here we are getting 3 columns and 2 rows. So what will be the target names? Here we are getting 3 values. So what will be the targeted values? The first one will be setosa, the second one will be versicolor, and the third or the final one will be virginica. So now finally let's plot the our concluding one, or the last one. Walaikum assalam. If you have any questions, you can ask me, or don't call me sir, you can call me by name, you can call me Himel. So we plotted the whole one. Here we can see that the first one will be Certosa, the second one will be versicolor, and the final or the concluding one will be virginica. So this was Where are you from? I am from Bangladesh, currently studying at Brack University in the computer science department in my second year. Do you have any other questions? So let us continue. So yeah, this is how we can see how we plot using PCA or principal components. So this here comes the conclusion of our the whole journey of the linear algebra for AI and ML. We covered the whole part what is needed for the machine learning and AI, which linear algebra parts was covered. If you have any questions, you can ask me, or